clear. All right, next, let's see. All right. So I got some questions. I got several different types of questions related to either superposition or Thevenin analysis. Now, of course, I believe, especially where we're going, Thevenin analysis is the most important of these methods to find to really understand. In my opinion, it's the simplest, but it also is very necessary to understand that for where we're going with capacitors and inductors. Now, I answered two questions a second ago, two or three. Somebody sent me an email question about superposition, I think. Who was it? No? I hate when I don't remember which one it was. I'm not going to look it up. No? Any questions? Let's try that approach about any of the homework. Now, you're going to need to understand Thevenin. What I'm trying to tell you is, I'm giving you a heads up. This stuff is going to come back to haunt you over and over and over and over again. So, how many tried the Thevenin analysis problems? I just need an idea of what I'm talking to. If you haven't, I encourage you to do them as soon as possible. You'll save your life doing them. I really mean it. It'll be so helpful for you. I would like to do one Thevenin analysis before we move in to transients on capacitors or inductors. And if you don't want to pick, I will. You got one for me? Anybody? Yeah.
You could do 3.45.
345. All right. Now that'll reference an earlier problem. All right, so 345, solve problem 3.1. Is that right? All right, 3.1. That's way back. Using Thevenin. All right, it's a start. I mean, it's probably a good problem. All right, so for this one, this is problem 3.1. And you've got a current source here. I'm going to show you another trick here you'll be thankful for in a second. This is 1K. And this is the current here that they're after I naught. Then 1K. And then 1K. And then another current of 2 milliamps. We're going to use Thevenin for this one. First, can everybody fall? Can you see it in the back? That's the most important thing that I've got to ask. Far back? Okay. So, in this problem, we're going to use Thevenin's analysis, all right? Now, hear me. The very first thing you do is identify the component that you want either the voltage or the current through. In this case, what is it? The 1K resistor. Does everybody see this? It's really, I'm just asking for a confirmation you can read it. So first step, RL is equal to 1K. And I've got a statement to make. Because people will get unsure about things. What if all of a sudden this wasn't what they were after? Suppose they were after V0 here. You all follow me? Yeah, V0. You with me? That's what they're after. But make it more complicated. Suppose now there were two 1K resistors. Do you all follow me? Now, if you just do this blindly, they say remove the load resistor. Well, which one to remove? Do you follow me? They're both identical, correct? How would you approach that using Thevenin? I'm asking for a reasonable answer. Just think about it. Anyone? What might you do if we're after voltage? Yes, sir.
Maybe combine the two resistors and
See what I'm talking about? Yes. Yes, make it 1/2 K, right? You all see that? How many do? Always use your brains. I mean, you're smart people. Don't make life difficult and don't be afraid. So obviously, if there were a 1/2 K, if we're after the voltage and you see two in parallel, if all I care about is voltage, then just make it 1/2 K and put plus to minus V out, then it would be obvious. Do y'all see that? That's the kind of reasonable things that engineers should be able to see and do without anybody telling them how to do it. I mean, this is, I don't know how to put this, but what you see that seems right is probably right. So I'm going to go back to the original problem, but I'm saying that because I know there's a lot of people that are almost afraid to do what they think is right because it might be wrong. Don't do that. Don't. So here, I'm going to take that out. Here's where it was. Now we put VOC down. So first, I remove the load resistance, and I call it the load, and I put it plus to minus, and now I have to find that voltage. Everybody with me? Make sure you see this. What's the next step? Got to find the voltage, right? So how would I find the voltage? Do I need to do anything funny here? Well, hear me. Take a good look at that and ask yourself, how would I solve that if I wanted that voltage? Now, I want you to answer this question. I'm going to see how much current is going this way. How much current is going that way, and the reason. How many, just show of hands, I'm not going to call on somebody. Anybody want to tell me how much current it is? You should all be able to see it's 6 milliamps. It can't go through there, it's an open circuit. So this is 6 milliamps, right? What's the voltage across here? If you can see it in the back, what is it? Anyway.
6 volts.
6 volts, right? 6 milliamps, 1K, 6 volts. How much current's going here? How many see it's 8 milliamps? Right? Has to. I got 6 coming this way, 2 coming this way. That means that's going to be 8 milliamps, right? What's the voltage here then? Anyone? How many see it's 8 volts? Far back, can you see it? I don't know how you can see. Your eyes must be great. So that's 8 volts. Therefore, what is VOC? Now, what did I tell you to do before last time? Start where? Anyone? Negative terminal, right? And can I go this way, class? Yes or no? Not maybe. Now, if we don't know this voltage, right? That's a current source. We don't know what voltage is across it. You with me? You can't sum voltages around a current source. We don't know the voltage. Which way do we have to go? Right? Can't go here. So I start the negative. What does this say? Voltage increase of 8, and this is a voltage of or 14 volts, right? You know, believe it or not, that I think is the very problem somebody asked me about. I don't know who it was, but I got this email. I tried to answer. You with me, class? Now I have that. What's the next thing I do? Anyone? Turn off the sources, right? How many remember that? Turn them off. All right, they're both current sources. What do we do to them? I erase them. You cross them out. They are not there. When you turn off a current source, it's like cutting the thing out of the circuit. With me? So I'm just going to erase them. Now, how much resistance is between this terminal and this terminal? You see they're in series. How many see they're in series? It's very important that you're honest with me. Do y'all see that or not back here? 2K. Do you agree with that? How many see it's 2K? All right, so it's 2K. R Thevenin equals 2K. Can somebody send me an email reminding me to complain again about this light? This is the most irritating thing when you're trying to talk and it's there, that it's not there. All right, now what's the last step, class? We're going to assemble the equivalent circuit. Now, the Thevenin equivalent circuit doesn't have a load. Doesn't matter what the load is now. But now I put the V open circuit here, all right, which happens to be 14 volts. Then I put the resistance in series. I'm going to show you a neat trick in a second. I put R Thevenin here, which was equal to 1K. No, I mean, sorry, R Thevenin was equal to 2K, my bad. And I show this. This is where, actually I want the current. Now that is the equivalent circuit. I want you to hear me now. This is why it's so nice to do it this way. At this point, I've taken that entire mess and I said, regardless of the value of the resistor here, the entire circuit that would cause that voltage can be reduced to simply a single voltage source and a single resistance. And now, no matter what resistance I put across that, I can easily obtain the voltage or current through it. How many see that? So now I can go through and tell you what it would be for 1K, 10K, 100K, a half a K, 0.5K. Y'all with me? Very easily. Now, but the next step is this is where the load voltage would be, or V out, and the current. Now I put the resistance back in, and that resistance is 1K. And now, in this case, they wanted the current through there. And what would that current be? I think you can all see this by this point. It's really going to be what? Just VOC divided by R Thevenin plus 1K, right? Does everybody see that? Specifically for this one, it's 14 volts divided by 3K, or 14 over 3 milliamps. And that would be the answer to that one. But it's important that you have an appreciation on how to do this. Now I'm going to show you a couple of other things that is very important. I'm going to erase this. Let me erase this and I'll show you something. This is called a Thevenin-Norton transform. I'm going to show you this. I don't even know what page it's on in the book. So let me get you a real eraser. There used to be erasers. Anybody see anything that looks like an eraser? Well, life goes on. Just do my best. And I'll tell you why this is so nice. So now, we're going to show you how you can do something that you can take a series resistor in parallel with a voltage and turn it into a parallel current source with the same resistance. Now, just hear me. So, if I have a voltage here that I'm just going to call V open circuit, and I have a resistance here, and I'll just call it R Thevenin. And then here is where I would find the actual output voltage or the output current. Y'all with me? That would be the equivalent Thevenin circuit for any combination of resistors and current sources. With me? Or voltage sources. You can always boil it down to that. But this is exactly equal to, I'm not going to prove this. I could, but exactly equal to a current source. This is called a Norton equivalent circuit. This is a Thevenin. In parallel with that resistance that I'm going to call R Thevenin. And here, you could attach the resistance. And the value of this IS here is equal to V open circuit divided by R Thevenin. Do you see this? I'm going to show you some examples, but why and why is so important. Also, I'm going to tell you a little bit more about Norton equivalent circuits and why they're so important to understand. Now, if you look at this, the best thing to do is first see an example that they are in fact equivalent for a given problem. You with me? Then I'll show you a little bit more about that and why it's so important. So I'm going to come over here and kind of work from our last example. Last time we had an open circuit voltage of, was it 14 volts? Is that right? For the problem we just did? Okay. So I'm going to show you this. So here we have 14 volts. And we had R Thevenin, and I think that was 2K, correct, class? And then I wanted, here's where my load was. I'm saying that that is equivalent to, I'm going to erase this and just put it right here. I'm saying it's equivalent to a Norton circuit. I'll show you a little bit more about this. And this would be equivalent, I'm going to do it right here. As I said, the IS here would be equal to the open circuit voltage 14 divided by R Thevenin, or 2K, or I short circuit would be 7 milliamps. So that's what this would be. 7 milliamps would be the current here. Can you all see that? Now you take R Thevenin, and instead of being in series, now it's in parallel. This would be 2K. I'm just going to put it like this. And now I'm going to attach the same load as before. You all follow me? I'm going to prove you get the same answers with both of them. So more to this, but I want you to see this part. So now when I put in 1K here, I knew that this current would be simply 14 over 3K amps, or really 14 thirds milliamp. How many see that, first of all? Make sure you see that, what I'm talking about. That's from last time. Now let's go over here. I say that I have 7 milliamps. I have 2K here. Now I put the load on here. And this was 1K. And I want this current, right? Let's see if they're the same. How would I get that current that I'm looking for? Anyway. We know this current, it flows into both. What do we use? Anyway. How many say it's current division? Are you with me? So with current division, it says you take the source current, IS, I'm going to put it down in a second, and you multiply it by the opposite value of resistance that you want the current through. I want the current through this guy, right? So I multiply by the opposite value first over the sum of the two, or 3K. Right? So therefore, I here is equal to 7 milliamps times 2 thirds, or 14 thirds milliamp. And if you look there, they're identical. How many see this? That means when you're doing problems, if for whatever reason you would prefer to have a current source in parallel with resistance, it is available to you. But more so than that, it also means one other thing. It means instead of getting the open circuit voltage like we've been doing, you can get what's called a short circuit current. Just take the load off and put a wire between the two terminals where the load was, and find out what the short circuit current is, and then you can take that and simply calculate the rest of the problem. You all with me, class? Short circuit current is what I'm showing you right here. If you get the short circuit current, goes right there, then you still have to calculate the R Thevenin, it goes in parallel. then put your real load there, and you can do it either way. Now, you don't appreciate the significance of that, but you'll see in many problems, getting the short circuit current, it's much easier than getting the open circuit voltage. Now, I can't say that every time, but it is true. And we'll go through more of this. I'm just showing you the options. These are Thevenin-Norton, write that down, Thevenin-Norton equivalent circuits. And in the book, he's going to be talking about them. Now, there's one thing I didn't cover yet, and I'm not going to cover it quite yet, and it's called finding the Thevenin equivalent circuit when you have dependent sources. In that case, the open circuit voltage is still the same, but to calculate R Thevenin, you literally have to put a voltage on the terminals that you remove the resistor and find the equivalent current caused by that from the actual voltage source that you put on. This is a little bit down the road. I'm not going to cover it right now. Now I'm going to move into chapter 3. The assumption is we have a thorough understanding, into the transient analysis for capacitors and inductors. That's chapter 4, I'm sorry. But that's where we're going now. So I just mentioned a bit about it. Now this stuff requires some attention. It is more complicated in a sense, but if you have a firm understanding of the latter, of the stuff we just covered, this shouldn't be much different. It shouldn't be that difficult. But it does require you to have a good understanding of the past stuff. So here we go. By the way, in fluids, do they have an equivalent to this that I just showed you or not? Pressure equivalent to flow? No? I bet you do, I just don't know what it's called. Norton, by the way, was an engineer at Bell Labs. Thevenin is a very famous French engineer. All right. So this is chapter 4. In chapter 4, we talk about capacitors and we talk about inductors. So the next thing I talk about is how to develop, first an appreciation of how you add capacitors in series or parallel. I want to focus on capacitors. I want to tell you one other thing. Yeah, first thing I'm going to do is show you how to find out the equivalent value of capacitors or inductors, and I'll get to that in a second, in series or parallel. You know how to do it with resistors, right? All right, you're going to find that was helpful. So capacitors, this is the symbol for a capacitor. The units of capacitance, does anybody know? You're right, farads. The units are farads. All right. Now, when you have capacitors, and this would be the equivalent value of the capacitance measured across those terminals. It's pretty obvious. It's just the value of a single capacitor. But if you think about it, what a capacitor actually is, it's really two plates, electrical plates, with a small space between them and a dielectric or an insulator between those plates. So no DC current can flow through it. What would you think happens if you had two of them in parallel based on? Matter of fact, I'll just tell you, for parallel plate capacitors, the formula for capacitance, the approximate formula, is the value epsilon. And epsilon is actually, I'm just going to go ahead and write it down, is epsilon naught times epsilon relative. And epsilon naught is, you don't have to know this, 8.854 times 10 to the minus 12 farads per meter approximately, and epsilon relative is greater than 1 or equal to 1, less than or equal to about 50,000 for exotic materials. So epsilon relative has to do with the amount of energy storage that could be available in capacitance. I'm not expecting you to know this, I'm stating this just for a little, more or less for completeness. So the energy stored in a capacitor is equal to 1/2 CV squared, where V would be the voltage. Energy here is in joules. C is the capacitance. How many remember that from physics? Y'all remember physics, right? You had to do energy, you had to do what? Current and stuff like that? LdIdt was the current through an inductor, CdVdt was the current through a capacitor. Those are like high school physics stuff you had to know in college, and you had to work with it. And remember, all of engineering in general is understanding physics and then applying it with the complicated mathematical methods we have to solve either design or analyze problems. And they're either integral differential equations or sum and difference equations. Because really, if you can't do that stuff, you're probably in the wrong major. That's the bread and butter of everything we do. You laugh, but I mean, the MEs, civils, whatever. Just look at anything. There are always these equations that come at you first. All right, so what happens? Here, I'm asking you this. This is C1. This is C2. This is C3. And dot, 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 all the way out to to the end here. What would the value of the equivalent capacitance here be, do you think? This is C if they are in parallel. First, you all see they're in parallel. Same voltage has to be across each. Just let me see your hands if you do. I don't like my drawing either, but it's as good as it gets. So, now, what do you think the capacitance of that is? Gut feel, think. Capacitance proportional to the area of the plates. What do you think happens to the area of the plates if they're effectively? Just increases, right? Distance doesn't separate. You add them as if they were in series. For the total capacitance here, C equivalent, it's just equal to C1 plus C2 plus dot, 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 plus C to the end. It's just the sum of all of them in parallel. Can you all see that? How many can? All right. Now, if they are in series, I'll put it right here. If you have them in series, and I want this value, now this is like resistors in parallel, all right? Because effectively, what you've done when you did this is you put a bigger gap in between all of them. That's effectively what you've done, whether you know it or not. There's more to that part, but it's the way I think about it. What that is, the total capacitance is 1 over C1 plus 1 over C2 plus 1 over C3 plus dot, 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 plus 1 over C to the n. Now, the thing about it is when they're in series, the total capacitance is always less than the largest value. Always. If you look at that form, it's like resistors in parallel. You all follow me, class? If you have resistors in parallel, the resistance is always less than the largest value. You all follow me? That's the way you add them. So the first sets of problems you get are very simple, and I might as well just do one. We'll look at the end of chapter 3. I'm sorry, chapter 4. Let's just take a look at problem 4.4. I'm going to ask you this. Now these things they're not that tricky, but people get a little confused at times with the drawing. I have a question for you that's been bugging me. How many have had just MATLAB in here for programming? How many have had C? C++, any version of C? What major?
Computer science.
All right, that would make sense. How many have had Python as a structured programming language? What course?
CS13.
Say again?
I did like a Georgia Tech math
All right, see, Python, I'm gonna level with you, is being used for just about all the AI stuff. And if you're smart, learn AI. I mean, you see ChatGPT, it's all over. I'm learning Python and how to apply it to AI. It's a lot like MATLAB, it's not that hard. But just a lot of the syntax is slightly different. I'm asking that because I don't even know anymore what's being taught to everybody. It used to be everybody learned Fortran, then C, now MATLAB. MATLAB's a great higher level language, but you have to pay for it. One last thing, how many know what Octave is? Octave is the free version of MATLAB. And I love it because that FlexLM license drives me nuts at times. It's called Octave. It's your best buddy if you don't want FlexLM or fork out some cash for a MATLAB license. You probably have the student version I take available to you. MATLAB is more powerful and faster, but if it's free, I'm not complaining. All right, so for this problem, this is 4-4. Here, they have A, and then they have a capacitor, and this is 3 microfarads. Micro is 10 to the minus 6. This capacitance is 2 microfarads. And then they have B over here. And they have 12 microfarads. And then, what do they have? 20. This comes down, comes over here. And they have 6 microfarads. And they have this. First, take a look at that. We're going to simplify this. Now, think first, identify what's in series, and then in parallel, and reduce the complexity. Hear me, class? Take a moment, and remember what I said. Capacitors in series, add like resistors in parallel. Capacitors in parallel, add like resistors in series. I showed you the actual mathematics a second ago. You all with me, class? Did they do this in physics, by the way? Okay, good. This should be something you see. Now, when I look at this, I'm going to ask you a question. I want you to write it down. All right. Let's see what we combine first, what is apparent to you. What about these two? Anyone? What are series? How many see series? All right. Therefore, they add like resistors in parallel, right? So it'd be 1 over 3 microfarads plus 1 over 6 microfarads. Take that. That's 3 over 6 microfarads. Flip it. That would be 2 microfarads. Or sorry. Let me do it this way. This is 1 over 3 microfarads, right? Plus 1 over 6 microfarads. So that is 2 microfarads. How many see that, first of all? You agree with me? Did I mess up? I'm not going to try not to mess up, but I may. All right, so now what I'm going to do is say for this circuit, I'm just going to erase them and replace that with 2 microfarads. You okay with that? All right, erase it. Microfarads. All right, now, next. What do I see next? Yes, sir. And here's something I'm going to show you. Maybe I can get away with it this time. Here's here's my, this is, I could be wrong about this, but I've always believed sometimes topology is the enemy of insight. So you don't see what's in parallel, what's in series maybe. I'm just going to say that and assume that. You got markers, you got colored pens, you got something. All right, I'm going to start here. And everything that touches that blue side here has got a certain potential. Do you agree with that? Now I'm going to go on the other side of one of these two. And I've got green here. Thankfully it works. And everything between the green and the blue is in parallel. How many see that? All right. Somebody said, can I use colored markers? They sent me an email. Of course. Or colored pens or colored pencils. Use it. It'll help you. After a while, you won't need them. So if they're in parallel, I'm going to do a redraw. You see that off of terminal A, I have this and this in parallel. Do you see that? So here's my terminal A. I just put it anywhere. And I'm going to have a parallel combination of 2 and 2, or parallel 4 microfarads. How many see that? Got 4 microfarads. Now, let's go to the green side. Now I'm on the other side of both of those, right? What's this? Series or parallel? Series, 12 microfarads. Now, you'll get good at this after a while. What is the equivalent capacitance? Take a look. They're in series. They're like resistors in parallel. How do you get it? 1 over, right? 1 over 4 plus 1 over 12. What is that? 1 over 4 over 12, or can't be right. What did I do wrong? Oh, 3. 3 microfarads, right? So the equivalent here is 3 microfarads. How many see this? I'm just doing a simple example to show you. Now, that's how you add capacitors in series or parallel. These are simple problems, but you have to know how to do them. Now I'm going to show you inductors, and you're going to love inductors because they add like resistors. You just did resistors. All right. That comes next. I'll do the differential stuff next time. By the way, the reason this is important is a lot of times you're going to look at something called a schematic, an electrical drawing of the circuit, and you're going to have to understand what the equivalent values are of capacitors or inductors in these circuits. All right, now we talk about inductors. So, the symbol for an inductor is just a coil like this. That's an inductor. The symbol is L. I should say the letter symbol is L. And the units are henries. Now, when you look at an inductor, the way I think of it is, think of a large coil of wire. That's all they usually are. You've had this in physics. The reason it's coiled is so it can concentrate the magnetic energy. It'll create a magnetic field around it, and the energy is stored in the magnetic field. You don't have to know this right now, but the actual magnetic energy, or the energy in this inductor, is 1/2 L, 1/2 L times I squared. So if there's a current going through here, that would be the magnetic energy in an inductor. Now all that energy we can get out, and we can get all the energy out of a capacitor too. And both have to do with the relative amount of either current or voltage. When you think about inductors, they add like resistors in series. So if you have an inductor L1, an inductor L2, and an inductor Ln all in series, the equivalent inductance here just adds them up. L1 plus L2 plus dot 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 plus Ln. Just like resistors. You've done resistors, this should be second nature. You with me? Now, if they're in parallel, thank you very much, they add like resistors in parallel. So if you have this, the equivalent inductance here is 1 over L1 plus 1 over L2 plus 1 over L3 plus dot 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 plus 1 over Ln. That's it. So I try to always do an example of both. I think this one sort of gives it away, but I'm gonna do problem 4-8, or you're gonna help me. Remember, they add just like resistors. So for problem 4-8, which I'm gonna do here, here's A and here's B. Millihenries, 8 millihenries. Twelve. And well, he actually does something different. He puts it up here. And what he wants to know is, what is the equivalent inductance here? So they're looking at this. L equivalent between these two terminals. Can everybody see this okay, class? Now, I always tell you to simplify the circuit. First, take a look at it. Don't just knee-jerk react. When you look at this thing, we could use the color method if you want. But you see this is in series, right? If anything else. Do you agree with that, class? Just show of hands if you do. This, the only way current gets the part from A anywhere is going through that 8 millihenries. Do you agree with that? So for the redraw, I'm going to put it over there. That's going to be 8 millihenries. I want to put it right here so you can see it. Here's terminal A. What next? Take a look for a second. Now I could get the colored markers out, but just take a look. Remember, topology means nothing. It's the electrical connections, right? Doesn't matter if the resistor or if the inductor's up this way, over that way, down this way. It's electrically how they're connected. Now at this point, from here to here is 8 millihenries. Do you agree? When you look at that, what about these two? Series? How many see it? What can I replace them with? 24. Do you agree with that? All right, I'm going to do that. All right. Now, your attention. Make sure you see it. This is where people get nervous. Well, it's horizontal, not vertical. Doesn't matter. It's how it's electrically connected. Can you see this is in parallel with this, in parallel with this? Show of hands. You see it? Far back, guys? All right? Take your moment. Remember, I can take this and slide it this way if vertical helps you, right? They're all in parallel, right? So I have 12 here in parallel. I'm going to get rid of that. That's done just to make sure the topology doesn't bother you. So that's 12 millihenries. Well, what would that equivalent be? It would be what? 1 over, I'm just going to leave this 12. 1 over 12 plus 1 over 8 plus 1 over 24, right? So what is that? That's 1 over, and this would be 1 plus 2 plus 3 over 24, right? So that's 24 over 6, right? Or 4 millihenries. Is that right, class? How many see that's 4 millihenries? Can you all see what I'm doing over here or not? So I'm going to replace that whole thing with 4 millihenries. I'm almost out of time. Last question. What is the equivalent now? How many see it? All right, I'm going to give you problems on this. This should be pretty second nature to you, but please take time to do it. Because assuming you know it may really hurt you. Make sure you can do it.